didn't get to this yesterday, but we are going to recap our main lesson points. We had 3 main learning topics for yesterday. One is making predictions. We use our line of best fit, or the least squares regression line, to make predictions. When we write the equation for the line of best fit, we want to put y in context here. So you should never just have a y hat. You should have what does y mean, and then with a hat over it. Equals a, that's my y-intercept, plus b, that's my slope, and then x. And you should have x in context inside parentheses so that we know what x means. That's actually the whole reason that we flip this around, because like algebra 1, it's y equals mx plus b. Because we write x in context, so we oftentimes have something that's pretty lengthy, we put it at the end. So all the numbers come right after the equal sign, and then our variable at the end. The residual, RAP. Residual is the actual minus predicted. And interpreting that, we would say the actual, whatever, was, whatever my residual is, above or below. So I'm never going to report a negative number here. I would use above or below to determine positive or negative. The predicted value for x equals, and then whatever my x is. Like whatever that value is. So 3 rubber bands or whatever. And then interpreting my y-intercept and my slope. When we are interpreting the y-intercept when x equals 0, whatever that means in context, the predicted, whatever y means in context, is, and then whatever my y-intercept is. Slope for every additional, for every one more x, the predicted y increases or decreases. That's where you do your positive or negative, and then whatever your slope is. I want to give you guys about 5 minutes to do the check your understanding down at the bottom of the page. You've got 5 questions, so that is about 1 minute each question-ish. So take about 5 minutes to work through that, and then we will go through that together. There you go. Get stuck, or just if you want to, you are allowed to work together with other people if you would like to on this.
What?
Yeah.
Oh, wait, it says it up here.
What is the slope? 160. How would you interpret that slope? For every what? For every mile, for every additional mile, or for every one more mile, for every one more x. So for every one more mile, the predicted calories burned increases by 160 calories. Absolutely. For each additional mile that is run, the predicted number of calories burned increases by 160 calories. Make sure you have that predicted in there. These lines of best fit, these least squares regression lines, the only thing they can do is make predictions. What is the y-intercept here? 20. Can we interpret this in context? Will it make sense? How would we interpret this? When he's at rest, or when he has run 0 miles, he's burned 20 calories? Super close. What can these lines do? What's the only thing these lines can do? Predict. So it's predicted that he burns 20 calories. When Michael runs 0 miles, or you could say when he is at rest, I would accept that, because he's not running if he's at rest. The predicted number of calories burned is 20 calories. How many calories is Michael predicted to burn if he runs 5 miles? 820 calories. I'll put that up on the screen here in just a second. 820 calories is the prediction. I want to make sure everybody has a chance to get this down before I scoot on. All right. 20 plus 160 times 5, 820 calories. Calculate and interpret the residual if his Apple Watch said that he actually burned 910 calories on a 5-mile run. How do you calculate the residual? Actual minus predicted. So what was the actual? 910. The predicted? 820 for a residual of 90. How would you interpret that then? Yes. Got 900. Let me look at what happened. You only multiply this. Yeah, in our equation, or sorry, just with this, because the x is just next to the 160. And then you add the 20 on top. How would we interpret a residual of 90?
Actual amount of calories was 90 calories above the predicted value for 5 miles run.
That's exactly right. The actual number of calories burned on a 5-mile run was 90 calories more than predicted. I like the way you organized your sentence better than mine. Michael is thinking about signing up for his first marathon. So far, his longest run has only been 10 miles. Should he use the regression equation to predict how many calories he would burn if he runs a marathon, which is 26.2 miles? Matthias says no. Why?
It's too far away from the data.
That's exactly right. It is too far away from the data collected. We would consider this extrapolation. You don't want to make predictions that are too far away from your collected data. They're not reliable predictions. Yes?
What is considered,
What's considered too far?
no, what's considered not so far?
Oh, not too far. In this case, like I don't have what the data is that he's collected, but it says that he's only been out for 10 miles. That's the farthest run he's ever had. So I would say like 11 miles, 12 miles, that'd probably be okay. Once you start getting into like 15 miles, I'd say that's, because that's, half as much again as what he's already collected. I want to make sure that if I go to plot these points, it's not that I've got this cluster here and then this one guy way out here. So it kind of depends on the context. But if it puts it within the general realm, usually the safest bet is for what we call interpolation. Not going to quiz you on that word. Interpolation is when you want to make predictions that are within the values that you've collected for. Maybe he measured a 2-mile run and a 4-mile run and a 6-mile run, and he wanted to predict what would it be for 3 miles. That's within the data that he has collected. So those are usually going to be fairly accurate predictions. Once we start getting outside of the data, either high or low, they become less and less reliable. All right, let's go ahead and flip over to page 11. Page 11. All right. So here, I've got some Monster energy drink stock prices for different years. And we've got our scatter plot here. How would you describe the overall form of this scatter plot? Looks approximately linear. All right, let's go ahead and write that down for number 1. This has a linear appearance to it. I would like for you guys now to use this equation right up here. That is our least squares regression equation, and I'll explain what all those words mean here in a little bit. I keep calling it the least squares regression equation. I'll explain that today. It's our line of best fit. I want you to use this line of best fit to predict the stock prices in 2010 and 2022. And then I want you to find the residual, the actual minus predicted. So I want you to do both of those things. I'm going to give you about 1 minute. Use the regression line to predict the stock price for 2010 and then also for 2022. And then I want you to calculate the residual. What's the prediction for 2010? 7-ish? Can anybody give me a little bit more precise than 7-ish? 7.4. 538.
Oh, that. Oh.
It's okay. Yep, we're just plugging it in. We are talking about stock prices here, though, right? If I'm talking about money, reasonably, how many decimal places out should I take this? 2. So we should probably round this off to what? 7.54. And then we're going to calculate the residual. How do you do residuals again? Actual minus predicted. What was the actual stock price in 2010? 3.68. We're going to do minus 7.54. And that gives us what? Negative 3.86 when we round it to 2 decimal places. What about for 2022? What's the prediction? 41.06. Again, if we round it to 2 decimal places, it'd be 41.06. It goes out a little further if you're doing it precisely. And so then to calculate the residual there, the actual minus the predicted, what was the actual in 2022? 45.01 minus 41.06 would give us a residual of what? 3.95. Nice. So before we go do the next part, I want to talk about these residuals. So the residuals are the distance away from that line of best fit. So here's 2010. This would be the residual for 2010. 2022, this would be our residual for 2022. What kind of number did we get for 2010 for the residual? A positive or a negative? Negative. How could I tell by looking at the graph that we were going to get a negative residual? It's below the line. And for 2022? Positive, it's above the line. So anywhere that I have a residual that is above the line, or sorry, anywhere that I have a point that's above the line, I would expect a positive residual. Anywhere that's below the line is going to have a negative residual. When we take those residuals and we square them, right, so this right here, these are my residuals. This distance here is my residual. What happens when you take a number and you square it? Becomes positive no matter what kind of number you had. So my negative residual would have a positive squared value. If I do that for every single one of these points, I calculate the residual and then I square it. Ooh, this one's tiny. And then I add those all up. The least squares regression line is the line that minimizes the sum. Sum means what? Addition. Sum means to add everything all up. Let me actually get all this drawn in here. There we go. Now I can talk. We take the sum of all those squared residuals, and the line that has the smallest sum is our least squares regression line. So this here is the least squares regression line. it gets abbreviated LSRL. And that is a standard abbreviation. Instead of writing out all 4 words every time, you don't have to write that. You can write LSRL for least squares regression line. So what the computer is doing in the background, what your calculator is doing in the background, when we feed it all this data in those lists like we learned how to do yesterday, and then we have it calculate that least squares regression line for us, it is calculating all the possible residuals for all these points with all the possible lines. It is adding those residuals together, and the line that has the smallest sum of all those squared residuals is our line of best fit. So far, so good? All right. Let's come down and look at number 4. And I made a boo-boo when I was making your notes. I grabbed the wrong table and put it here. So I need you guys to fill in these pieces. I'm not going to make you calculate all of it, but I want you to fill in those pieces, and I need you to fix the years on the graph also. That was my big bad there. I grabbed a table for something entirely different. Sorry. So what I did to get this table, oh, did you have a question? Okay. What I did to get this table, these stock prices are exactly the same as what's up above. I just recopied them from that table that's at the top left of the page. For the prediction, how did I get those numbers for the predictions? Yep. I plugged them into that least squares regression equation, and you guys actually calculated 2 of these. What was the prediction for 2010? 7.54. And then what was our prediction for 2022? 41.06. And then I calculated the residuals for all of these. I did the actual stock price minus the predicted stock price to get my residual. Actual minus predicted to get the residual. What was the residual for 2010? Negative 3.86. What about for 2022? 3.95. What I want to do now is I want to take the year numbers, and if you haven't already, you're going to need to fix those on the graph because I grabbed, like I said, I just grabbed all the wrong things. The year numbers are going to be on the x-axis. And I want to plot the residuals on the y. So we have our xy pairs. This is called a residual plot. And I changed the scale on the y-axis too. On your page, it's counting by ones. We're going to count by twos so that we can fit all of these on our graph. So the first year that we have data for is 2006. We have a residual of 6.48. So it's up here somewhere. For 2008, we had a residual of 0.78, so here-ish. And then negative 3.86 in 2010. Negative 5.22 in 2012. Negative 0.37 in 2014, so really close to that x-axis. Negative 0.96, so about-ish here in 2016. Wait, did I miss a year? Yeah, I missed the 3.14. Sorry, let me go back and get the ones. I had 3.86, then negative 3.14. So 2012 is here-ish. And then we had 2014 that was at the negative 5.22. Negative 0.37. Negative 0.96. 1.25. And 3.95 is almost at 4. So up here. And that's where our data stops. For which points was the actual greater than the predicted? For what years was actual greater than predicted? So what were the years again? Where actual was greater than predicted? 2006, 2008, 20, and 22. Greater than predicted was 2006, 2008, 2020, and 2022. So basically, the actual is greater than the predicted. Oops. Where on this graph? Like, how can I tell just by glancing at this graph where the actual is greater than the predicted? Yep, where it's above the x-axis. These ones here and these ones here. My actual is greater than my predicted. So for what years is the actual less than the predicted? Yep, 2010, 2012, 2014, 2016, 2018. My actual was less than my predicted down here. Do you guys notice any kind of a pattern in those residuals? What'd you say? It's got a U shape to it. Absolutely. Residual plot has a curved pattern. It's got a U shape. It starts positive residuals, then we've got some negative residuals, and then it ends positive residuals again. Because that residual plot has a pattern to it, a linear model is probably not the best model. In fact, what I look for in my residual plot is no pattern. If there's no real discernible pattern, if it's just kind of random scatter, some are above, some are below, it's not like all the ones at the beginning are above and all the ones in the middle are below and all the ones at the end are above. At the beginning, some are high, some are low. In the middle, some are high, some are low. At the end, some are high, some are low. That's what I'm looking for this to be a good fit for a linear model. So, do you remember back on question 1? What did you tell me the general form was there? Linear. Well, based on this residual plot, it's nonlinear. Because the residual plot has a pattern. Tomorrow, we'll talk about what some of those other models are. But for right now, I just want you guys to walk away with the idea that if that residual plot has a pattern to it, the linear model is not the best model. Let's go ahead and flip this over to page 12. Two main learning topics for today. Least squares regression line, the LSRL. What that means, this line minimizes the sum of the squared residuals. This is what the computer or the calculator, that statistical software, is doing in the background. It is calculating all of the residuals for every possible line. It is squaring those residuals and then it's adding them together. The one that wins is the one with the smallest sum. And then residual plots. If I have a leftover U shape, or an upside down U, or a sideways Christmas tree pattern, those are bad. That means a linear model is not a good fit. I'm looking for something that's very randomly scattered. Some above, some below, some above, some below. It should be kind of going back and forth-ish between above and below. I'm going to give you guys, let's take about 4 minutes, since we got 4 questions here on the check your understanding. Take about 4 minutes to work through those, and then we will go through them together. You can work together if you want to. That is perfectly appropriate. word should you help you with? What word should you use to help you with number 1? What's the acronym? DUFS. What does it stand for? Direction. What's the U? Unusual features. F. Form. S. Strength. And there's one more thing that we have to make sure to get in there. Context. So what's our context here? What is this showing me a relationship between? City fuel economy, highway fuel economy. So I would say that the relationship between city and highway fuel economy is, let's walk through DUFs. How would you describe the direction of this? Positive. Are there any unusual features or unusual points that stand out to you? Not really. F, form. Looks linear to me. Even if you take that line out of the background, all these points are kind of lining up. And what about strength? I call it strong, fairly strong, moderately strong, somewhere in there. It's not weak. It has this linear shape to it, so it's not weak. So I would probably describe this by saying there is a moderately strong, positive linear relationship between city and highway fuel economy with no unusual points. The order that you talk about these things does not matter. You just have to make sure to hit all 4 of those pieces. You can do it in one sentence, you can do it in multiple sentences. The least squares regression line has the form of y hat equals a plus bx. What does the hat on y mean? Predicted. What is our y variable? What's being shown on the y-axis? Highway fuel economy. So this is going to be highway fuel economy hat, or the predicted highway fuel economy, equals, where do we get A from? The constant. When you look at the graph, sorry, not the graph, but these summary statistics back here, it's coming from these coefficients. The constant coefficient, that's A. I know it has to go with the constant because there's no variable. When my variable changes, this stays the same. That's why it's called the constant. And so then where do we get B from? Yep, right next to where it says city fuel economy. So highway fuel economy hat equals 1.151 plus 1.469 times X. What's X? City fuel economy. What is meant when we say least squares regression line? What is least squares? What? I can't hear you, I'm sorry. Best fit line. When we say least squares, it's minimizing the sum of the squared residuals. You're right, it is the best fit line. But the reason it's the best fit line is it has minimized the sum of all the squared residuals. What does the residual plot indicate about the appropriateness of the linear model? Let's go look at the residual plot. Is there a U-shaped pattern here in the residual plot? Sideways Christmas tree? Not really. I've got below, above, above, below, below, above. It's kind of bouncing back and forth. Do you think a linear model would be appropriate here? Yes. Residual plot has no clear pattern. It is randomly scattered, which means the line is a good model for making predictions. Little bit of housekeeping right before the bell. Monday is when we are going to bungee jump Barbie. We're going to talk about what the different types of models are tomorrow, and you'll have Friday to play around with that a little bit more. Over the weekend, you'll need to coordinate with your group so you can figure out how many rubber bands you're going to need. Also, because we're doing the bungee jump on Monday, I had to push your test to the following Monday. It is not on Friday the 13th anymore. It is now on Monday the 16th.